Welcome to Math341. I think this is lecture 25. This is the last class of the semester. And so what I wanted to do, as I was mentioning, is just review some material you should have seen in previous classes, review some of the material we've done in this class, which you should remember, and then just see, once again, applications. What do you think we're going to do later today? Good, right? It's this deep in a class with Professor Miller, and the title slide says Introduction to Logarithms. So almost surely we will be doing logarithms. If you just have one or two really good tricks, techniques, you can make a really good career. It's like the old joke, one lawyer in a small town doesn't make a good living, but two can live quite comfortably. Once you can get two things you can do well, you're in great shape. Taking logarithms is one of the things I really want you to know. So hopefully at some point in your life, you had a class where they gave the who gives a shit lecture. Why do we care about logarithms? The two big reasons is it allows us to discuss objects that span tremendous orders of magnitude from each other. And the other is it linearizes a lot of nonlinear functions. And tools like calculus become available. So this is not a smudge on the screen, although some of the other ones might be. That is the Earth on scale to the sun, and there's a little dot for the moon. How do you talk about things that differ by this many orders of magnitude? And then the other ones are some of the plots we've seen from the previous least squares lecture, just linearizing data. Why we care so much about logarithms. So you should have seen this before. If x is b to the y, then the log of x base b equals y. And so, I'm not going to go into too much detail. This is just the slides are here just for completeness. And here is a really nice one. I should have explicitly listed where I pulled this from the web, but just a bunch of things going from the radius of a proton at 10 to the negative 15 to the radius of the visible universe, if you have terrific eyesight, 10 to the 26. This is almost 40 orders of magnitude. And to be able to talk about these and draw them on the same scale is phenomenal. Okay. Can somebody give me examples of logarithms in the real world? Data that's measured in logarithms. pH, good, from chemistry. Floating point operations. I'm sorry, earthquakes, yes. So earthquake frequency and destructive power, the pH scale from chemistry. There's another one. Decibel, oh, I went forward too. Okay. I thought I had only gone forward once. Yes, decibels is another one. And again, it's just when you have certain quantities that span many orders of magnitude, you need a scale that is appropriate for something like this. Oh, no, I didn't go too far. I just had them in a different order. I had decibels before the pH scale. All right, that's on me. All right, so we know the definition of logarithms. We know how to calculate simple logarithms. If 100 is 10 squared, then the log of 100 base 10 is equal to 2. Once you enter college, log means what? Log base e. In college, we never really do things other than base e unless we're doing computer science, in which case then we want to do things base 2. But in college, we use base e because now calculus is nice. The derivative of the natural log is 1 over x. You don't have to have this fact of the log of the natural log of b floating around. Okay, so why do we care? So here's just a couple of plots of what's going on. 2 to the x, e to the x, and 10 to the x. I can't really show all of them on the same scale because they grow at such rapidly different rates that it's just not possible. We talked about why that. So let's look at some functions like x to the 4th, x squared, x to the 1/2, x to the 1/4. And if I'm looking at this, even if I just look at the top two of them, say x squared and x to the 0.5, it's really hard to see differences in behavior. And when we look at all 4 of them, 3 of them basically are indistinguishable. They're this kind of blurry line on the bottom. If we take logarithms, however, we can start to see the differences. So the one on the left is a semi-log plot. We're plotting the log of x to the r against x. And on the right, we're doing a log-log plot. And on the log-log plot, we now have a straight line. And now we can really look at the differences between the various functions. So there's a couple of log laws you should know. The first is the exponents law. B to the m b to the n is b to the n plus n. So once we have laws for exponents, these can be converted to laws for logarithms. Oh, I forgot to bring the slide rule up. If anybody is interested, I have inherited a large number of slide rules from my parents and great uncles and whatnot. She's technically my first cousin once removed. She was a physicist. I don't know if she had a slide rule. Slide rules were phenomenal in terms of what they could do concisely. They're put to shame by what we have now, but for a long period of time, this was the tool of choice, and you would even have belts to put your slide rule on that you could take it out quickly. I sadly do not have a really good gun belt for the slide rule, but it is an interesting exercise to see how these work. If anybody's curious, I have a bunch in my office. And so we have a bunch of log laws, these are listed on the bottom. They should all look familiar. The one that people forget the most is the change of base on the bottom. The log of x base b is the log of x base c divided by the log of b base c. In high school, this one is not really emphasized nearly enough. The purpose of that is to show you that you only need to know logarithms in one base. Once you know logarithms in one base, you have them in everything. This is very similar to this idea of standardization we have when we are looking at, the sample mean. We subtract off what we expect it to converge to, we divide by the correct scale, and now we have something that we hope will converge to a standard normal. So this is absolutely wonderful. In the old days, people professionally calculated logarithms. They calculated values of the normal distribution. They calculated digits of pi. And if you think that's bad, there were people who checked the calculations of the people who calculated these things. And there was somebody who had calculated pi to, I think, 700 digits, and somebody found a mistake at digit 500, which means all of the subsequent stuff is wrong. Interestingly, there is a formula for digits of pi base 16, where I believe you can jump to whatever digit you want. You don't have to pre-compute earlier digits. It's an amazing formula. All right. You should know how to prove these log laws. I'm not going to go through all the proofs. The proofs are on the slides, and so the slides are going to be posted so you can look at that. It basically just comes from unwinding the definitions. Given that some of you might move on to real analysis or abstract algebra, it's not bad for us to spend some of our last moments together talking about how do you prove something. One of the big proof techniques is write the given. Write what you're told. And at the bottom of the page, write your goal, write what you're trying to get to. And then try to figure out, how can I get from what I'm given? When you are young, your professors are kind if they are not named Miller. By that, I mean, they probably won't give you more information than you need. So if they give you something, it's either absolutely essential or it leads to an easier proof. There's not going to be too much extraneous information. There definitely won't be missing information unless they make a mistake. Later in life, that's not necessarily the case, and things get a lot harder. So if we want to try to prove the log of x to the n is n times the log of x, well, we know the log of x base b equals y means x equals b to the y. We want to calculate x to the n. It's screaming at you, please raise both sides to the nth power. So x to the n is by to the n, and now we use one of our exponent properties. B to the y to the n is b to the ny. That's the same as multiplying the exponents. If things are integers, there's a nice interpretation. If I have b to the y n times, then I get y factors from the first, y factors from the second, y factors from the third, and you can see why it's going to just be y times n. I will now, by definition, if I just take the logarithm of both sides, I get the log. The n went down. Oh well, it should be an exponent n. This does sometimes happen when I move things over to the iPad. So it should be the log base b of x to the n is n times y is going to be n times the log of x base b. Similarly, we can do the log of a product is the sum of the logs. I'm not going to go through the proof of that. It's pretty similar. Again, just unwind the definitions and use the corresponding exponent law. This is very similar to Calc 2 to Calc 1. The differentiation rules of Calc 1 become the integration rules of Calc 2. Then the last is the change of base formula, which is the most enjoyable of all of them. And I'll just leave the list there. It's just unwind. I believe we did prove this earlier in the semester. But again, when you know what you're trying to prove, it's not so bad. You just try to find ways to get from the start to the finish. We talked a little bit about n factorial a couple of times and just how rapidly this function grows. So I just, plotted it. I love the plot on the left. Things of size 10 to the 295, and you basically can't discern it from 0, then it shoots up, and then it's already off the charts. If I do a semi-log plot, if I do a log-log plot, even on a log-log plot, this thing is growing rapidly. And the reason is the log, that should be a log of n factorial, sorry. The log of n factorial is n over e log n. So it's growing faster than linear, but slower than what? Slower than, yeah, growing slower than n squared, growing slower than quadratic. So the log of n factorial is growing faster than linear, slower than quadratic. And again, this gives us a sense of how we can look at these things and get a sense of what's going on. All right, so what I want to end today with is another example of having different parts of your life all meet together. So this is something I've used in classes. This is something I've used with my children. This is something I have used in math outreach. This is a version of a talk I gave at a gathering of Massachusetts math teachers. Anybody know what movie this is spoofing? From M&M's to Mathematics, or How I Learned to Answer Questions and Help My Kids Love Math. We Cannot Afford a Mineshaft Gap. Dr. Strangelove, anybody? It's always interesting to see which cultural movies have survived. Okay. So when I was asked to talk to the math teachers, one of the big things is the world is changing. And it's interesting looking at these slides now a decade later as to how much has the world changed in those 10 years. I don't know how recognizable things will be in another 10 years from now with the machine learning AI coming in. All of you should be learning as much of that as you can. We are still struggling as a society in terms of how are we going to deal with it. Different schools have different philosophies as to whether or not we allow you to use it. It's going to be used. And so if you don't know how to use it, you will be at a competitive disadvantage relative to the other people who know how to use it. It is a powerful tool. Learn how to use it. There is so much data that's out there, but you have to know how to ask the right questions. You have to know, are the answers reasonable? Because sometimes they spit back garbage. So be very aware of that. So I want you to be looking for connections and trying to see how can you take a new problem and convert it to something you know. And what's that one thing we know from this class, from a class with Miller? Take logarithms, right? So, that's got to be lurking in the background whenever we have anything. All right, so we want to ask questions, we want to gather data. I like to use games to highlight and excite people about mathematics. So this was done back when 12 years ago. So my son was 6 and my daughter was 4, although it really began when my son was 4 and my daughter was 2. So I'm going to describe the MandMGame. So my kids were at a suboptimal daycare. And so I would often pick them up very early to get them out of there, and we would do various things. And so when my son was 4, he asked me one day, if you're born on the same day, do you die on the same day as someone? And this was a really good question. So how do you explain randomness to a 4-year-old? Well, I have an advantage that other parents don't have. My wife is an identical twin. Look, Aunt Sarah's dead, but Mommy's okay. No, can't do that. Okay. There's many reasons why you can't do that, but it would be a proof. So I wanted I won't say better, I wanted a different way to explain randomness to my son. And so we came up with the MandMGame. So everybody starts off with the same number of M&Ms. We did 5 because with the little crappy bag of M&Ms I had in my bag, that was as much as I could do. And we all tossed a fair coin at the same time. And if it landed on a head, you ate an M&M. If it landed on a tail, you didn't. My daughter still remembers the game she played where she got 5 straight heads and got to eat her M&Ms as fast as possible. Do you notice anything about the M&Ms? Well, what do you notice about this piece of paper? Let's see how observant you are. What do you notice? It's okay if it doesn't matter. Just what do you notice? Different colors. So what do you notice about the colors? Yeah, Kayla has all the blues. What do you notice about Cam's M&Ms? This depends. They're alternating, and the dad, not surprisingly, has the leftovers. Do you notice anything else? You know, Kayla was 2, Cameron was 4. I was older. So good, they're increasing rate of age. What else do you notice about the writing?
Oh, Cam is written by Cam.
Cam is written by Cam.
Oh, okay.
Right? Cam was 4. And yeah, I wrote Kayla's name. You know, I think both of my kids knew how to type their name before they could write their name. Society has changed. Do you think it matters what color M&Ms you get? I would tend to agree with you, but when you're playing with a 2-year-old, you roll with it. So what are natural questions you could ask about this game? So we have a game. Everybody gets, you know, some number of M&Ms. Toss a fair coin. What's a natural question you could ask about the game? Good. So does this game model the real world problem it's supposed to? What could you ask about the game itself? Good. What's the chance I win? And we'll count victory as winning. But of course, what does it mean if you eat all your M&Ms? Technically means you're dead. So I was explaining this to one of my son's friend's grandmothers at a birthday party, and she really liked it. And she was a children's book writer, and she wanted to use this in one of her books, but she didn't like this focus on death. I said, well, no, I'm sorry. You know, I'm a purist. The game was created with death. You know, I don't believe in coddling the, but if you want to do a Cheerio version, you know, we can do Cheerios with life or something. So natural question is, you know, how likely is a tie? How likely is it for someone to win? What if you have more people? What if you have a biased coin? So I've worked on variants of this with, you know, students at Williams, with students all over the world, with people in elementary school. And then, you know, it says so on the bottom, but by now you should know the very last line is one of your go-tos. Gather data. And so if we had more people, we would actually play. We would take M&Ms, toss coins. And so I'll put the M&Ms out. I know it's early in the day. If nobody wants to eat M&Ms, that's fine. I'll just put them out. So I'll put this between 3 of you. And I'll give you one to push back. And so put one between the 2 of you, put one back. Okay, so let's gather some data. So here is the results of playing the game or doing the theoretical calculation with 2 M&Ms. I'm sorry, with 1 M&M, there's a 33% chance of a tie, 2 M&Ms, 19% roughly, 3 M&Ms, 14%, and I went all the way up to 20. Is anybody able to look at this and predict what's going to happen in the future? And again, with small amounts of data, it is unclear if you have gone far enough to see limiting behavior, right? So what should we do? Gather more data, right? So let's gather more data. So let's go all the way out to 110. Why 110? Because it was the 110th meeting of the society I was speaking at. So whenever possible, you try to use stuff like that in your talks. All right, so we were celebrating 110 years of service. What do you think happens in the limit? What do you think the probability of a tie is in the limit? 0. But if you look at this plot, what would you guess? Does it look like it's stabilizing? Yeah, it's going to 0 so slowly that it does kind of look like it's. I was just at a conference in honor of the 80th birthdays of Carl Pomerantz and Mel Nathanson. And I think it was Pomerantz who once said the function log x or log x goes to infinity, but so slowly no one has ever observed it. And this is getting smaller, but at a slow rate. And so you might think it stabilizes and there's some kind of asymptote. How do you think we should look at this data? What should we do? Take the logarithm, right? You know, it's been almost 20 minutes and we haven't taken a logarithm yet for real. Let's take a logarithm, all right? So if we take the logarithm, what does that look like? A line. A lot of people say straight line. I don't know. I guess you could talk maybe about, if you're on a sphere, do you consider a line the geodesic connecting 2 points? But so this looks like a line. Do you think it's a perfect line? No, and if you take line detector, and so for those of you who are watching at home, it's kind of tough to see, but just take a long straight line and you try to put it on, you'll see that it's not quite perfect. Those few points in the beginning are a little bit off what is looking like the line in the end, which maybe is not surprising. Maybe it takes a while before the limiting behavior settles in. Similar to n factorial, it takes a while before things settle in. We can calculate the best fit line. It's drawn over here. And the problem is, because of the method of least squares, if you have something that's a little bit off, that has a huge pull. And so I get my best fit line for the log of the probability of a tie versus the log of the number of M&Ms. And so when I exponentiate it, I get the probability of a tie with 2 people, fair coins, k M&Ms, is about 0.2412 divided by k to the 0.5426. So if I plug in 220, I get the probability of a tie is 0.01274. The correct answer is 0.0137. Now, when I say what gives, do you think that's a positive remark about what I'm doing or a negative remark? Negative, right? Does that have to be a negative remark when I say what gives? No, but you interpret it as a negative remark. Did I do a good job or not? It seems pretty good. And again, this is also why we need better ways than, seems good, looks close. One thing you could do is you could look at percent error. So they're both small numbers. What if I just said the probability is 0? Okay, that's not going to be as good as over here, but it's not horrible. And so how much am I off by? Well, say it's about 1.27 versus 1.37, maybe on the order of 10%, 8%. So it's not horrible. It's order of magnitude, but it's not terrific. And why do you think it's doing such a bad job? So what should we do? Remove them. Throw them away. So let's just go from 50 to 110. And so if we just go from 50 to 110, I will zoom in and you can see the straight line. That is a good straight line. And so now it's slightly different exponent 0.50553, slightly different constant. And now if I plug in 220, I get 0.01344 versus 0.01347. That's not bad. To be predicting this well from just gathering some data from 50 to 110. And again, I don't need to gather every point from 50 to 110. I just heard a talk on missing data, which is sadly something that a lot of you will be facing in the future. What if you don't have all the data you want? How well can you do? This is a richness of data that we're often not going to have. I don't need this much data to get this good of a predictive line. Okay, so this should remind you, just like in the last class on German tank, we did the birthday problem, which was one of the very first things we did. Today we'll do the geometric series formula. And in honor of the Celtics, remembering that a basketball game has 4 quarters and not 3, we will go back to Larry Bird and Magic Johnson. And so we did this before, so that they're going to alternate shooting. Bird always gets a basket, probability P. Magic always gets a basket with probability Q. First basket wins. Call X the probability that Bird wins. We want to find X. This was one of the first things we did. It's worth repeating because this is such a great idea. It's coming up with a recursive formula that allows us to solve for the unknown by getting it on both sides. So we can break it into cases. I'm not going to go through in as much detail as before, where the probability he wins on the first shot is P, and then on the Bird's nth shot, then he and Magic have to have n-1 misses, and then it has to end with Bird with a success. So if we let R be the probability that they both miss one after the other, 1 minus P, 1 minus Q, we get the geometric series formula. So the probability Bird wins is P times 1 plus R squared plus R cubed and so on. So if you remember the geometric series formula, you're done. But you can actually use this as a way to find the geometric series formula and talk about memoryless processes. For a lot of things, all that matters is where are you, not how did you get there. In a chess game, it matters how you get there. A threefold repetition of board positions is a draw. And when my son and I play chess, we haven't played in a while, his goal is not to lose to me. My goal is not to lose to him. We're both happy with the draw, because with the draw, I can say, you didn't beat me. And with the draw, he can say, and you didn't beat me. And so a lot of times, we will both go for that threefold repetition because we can get out of it. So if we want to calculate the probability Bird either wins by getting the basket on his first shot, probability P, or they both miss, 1 minus P, 1 minus Q, and then it's like we've reset the game. And then it's just an X from there. And now we have X on both sides. This is the bring it over method. And now we can solve for X. And so when we do the algebra, we get X is P times the geometric series formula. And we just found that X is P over 1 minus R. So we can deduce the geometric series formula. It's worth noting that we only proved this when R is the product of two probabilities. You can adjust this method if R is negative, but not if R is complex, unless it's a really nice complex number, if it's a root of unity, if that means anything to you. Okay, so things I want you to get from this is the power of looking at something as a memoryless process, of reducing it to something previous with a recursive argument. We can often circumvent painful algebra by looking at the problem the right way. This is a really good idea. You don't want to do infinite sums. Finite sums are much better. Sometimes the problem is not as difficult as it might look if you can find the right way to look at it. And that's the challenge. And this is one of the things with machine learning and AI is going to be absolutely phenomenal. They can try billions and trillions of things. Whereas we have to go through some kind of divine inspiration of what path we want to take. All right, so let's revisit the MandMGame. Here is the formula for the probability of a tie. It's an infinite sum involving products of binomial coefficients and powers of 1/2. Okay? And if you've done some advanced mathematics, this simplifies it, I'll put that in quotes, to a special value of a hypergeometric function. Just because I've given something a name does not mean I can work with it. Yeah, the only way I can calculate sines and cosines is through an infinite series expansion for a general angle. We accept that. We accept sine and cosine as a good function. We don't accept the error function c as a good function, or as a good function. I'll probably talk about this in a little bit, but this is actually a very reasonable formula. If you think about what's going on, each M&M is, each coin toss is going to be a head or a tail with probability 1/2. If there's a tie, we have to have exactly n tosses, where n is at least k, the number of M&Ms. So n could be k, k plus 1, k plus 2, k plus 3. How can you have a tie? You either have a tie on k tosses, k plus 1, k plus 2. They're all disjoint possibilities. So the probability of a disjoint union is the sum of the probabilities. Again, reviewing concepts from the class. What is the probability you have a tie on exactly n tosses? Well, the last toss for both of them has to be a head. That's the factors of 1/2. The previous tosses, each person has to get k minus 1 heads in the first n minus 1 tosses. That's the n minus 1 choose k minus 1. And because heads and tails are both equally likely with probability 1/2, that's why you have 1/2 to the n minus 1. It's really 1/2 to the k minus 1, 1/2 to the n minus 1 minus k minus 1. So the formula is actually quite reasonable. But when you look at this, if you can see what this looks like as k gets large, good for you. Looking at this, I don't really see the large term behavior from this. So there's another way to look at this. There are 4 possibilities. Both can eat an M&M, just Cam, just Kayla, or neither. Each of these happens a quarter of the time. And then, as I was remarking, each person has to have exactly k minus 1 heads in the first n minus 1 tosses. We get our formula like this. Do you really want to view it as there are 4 equally likely options? Or is one of these options a little bit different than the others? I was expecting to take a little bit longer for someone to say that so I could take a drink. But yes, why is neither eats different? Good. You could deny the each, might as well just forget that that happens. Don't consider that an option. I think we did the log5 method in baseball with two teams playing. They either have a good day or a bad day. And we had this formula involving P's and Q's for what's the probability one team beats another. And we can eliminate the case when they both have a good day, both have a bad day. And we got this conditional probability argument. It's the same thing here. If neither one eats, it's as if it didn't happen. In the real world, if neither one eats for a long period of time, that's a separate issue. So memoryless process. Now the game is finite. Why is the game finite? We start with 2K M&Ms, and on each turn, at least one M&M is eaten. So we've now reduced it to a finite game. And so now I'm not going to do the calculations. I will leave it to you to show that this is the probability of winning, I'm sorry, of ending in a tie now. Absolutely wonderful. We've reduced an infinite problem to a finite problem that I can calculate exactly in a very small amount of time. Okay. There's other ways to view this. Why do you think I'm saying Cam has C M&Ms and Kayla has K M&Ms? Yeah, the start of their names, right? Why do we use the sign we do for integral? Why do we use the sign we use for sum? Yeah, the integral looks like a, not an I, an S. The integral looks like an S. And why do we use the sigma notation for a sum? Yeah, the letter sigma is the S, right? You want good notation. You want to be able to quickly glance down and see, why did people choose this? We use a capital F for the antiderivative. We use an F prime for the derivative. So you can quickly see that it's related to this function F. Notation matters. 2 days ago was the, I think, 12th anniversary of the best thesis defense I think that was ever given at Williams. If people are interested, at the end of today's talk, I will show you their slides. Incredible amounts of information. And how do you present that information in a way that is understandable? Since it's not my thesis, I don't think he would have any problems with me showing it, but I will not record that without his permission. All right. So each turn, one of three things happens with probability 1/3. We go from CK to C minus 1, K minus 1, or to C minus 1K, or to C K minus 1. We can represent this as a flow. So let's start off with 4 M&Ms for each, and we have to end up with 0 M&Ms for each. Why am I not doing 5 M&Ms? Because the table's already getting quite big, and I want to make sure people can see it, okay? And so I look at all the different ways. So at each turn, if I'm at 3-2, I can go from 3-2 to 3-1 to 2-1 or to 2-2. And I look at all the different paths and I see how often do I end up at 0-0. What's the only way we can get to 0-0? From 1-1. Now, I could technically get to 0-0 from 1-0, but as soon as I hit 1-0, one person is out of M&Ms and the game is over. I don't have to worry about that. I really only have to calculate what's the probability I get to 1-1. And then once I get to 1-1, it's just 1/3 of the time I'll get to 0-0. So let's do it slowly. We start off at 4-4, and then 1/3 of the time we move to either 4-3, 3-3, or 3-4. And now for each one of these, we can see what happens next. Now, in terms of figuring out what happens next, the 4-3 goes down and to the right to 3-3. The 3-4 goes down and to the left to 3-3. So I'll send the 4-3 and the 3-4 down first, and I'll increase the probability of being at 3-3, and then I'll send that down. And so when I do that, I then can calculate what's the probability I'm in the next level. And I can then do a similar argument, and I can calculate, and I'm going to just do it very slowly. I'll start off with the two extremes, the 4-2 and the 2-4. 2/3 of the time I move down a level, 1/3 of the time I either move to the left or the right. And then I just keep going for each one of these. 2/3 of the time I move down, 1/3 of the time I move left or right. And then I look at my new probability of being at 2-2, and then that goes down. And then I have this level. And now if I want to get to 1-1, the only way I can get to 1-1 is how? So what's the only way I can get to 1, 1 from this row?
2, 2, double.
So from 2, 2 down to 1, right, but I'm in this row from 4, 1 all the way to 1, 4. How can I get to 1, 1? I'm sorry?
2, 1, and 1, 2.
Could I get to 1, 1 from 3, 1? So I agree that if I have 2, 1 and Cam meets an M&M, I can go to 1, 1. And Cam comes before Caleb because alphabetically C comes before K. Could the 3, 1 get to 1, 1? Yeah, first Cam meets an M&M and Kayla doesn't, and then Cam meets another one. So I do actually have to worry about all of these with just Cam or just Kayla eating. And so, we just play the same game as before, and I only care about the probability that's going to the left or the right, and I keep playing like this, and at the end, I get 245 over 729 is the probability I'm at 1, 1, so it's just going to be 1/3 of that to go down to 0, 0. Okay, so we've talked about generating functions, we've talked about binomials, Fibonacci numbers, and we talked about how to write down a closed form expression for the Fibonacci's. They satisfy a beautiful recurrence relation. And we have techniques to solve and find closed form expressions like this. What's wonderful is I can now see that the Fibonacci's are exponentially growing. I can get a sense of what their rate is. I can do a tremendous amount from something like this. I'm solving the recurrence relation. Is there a recurrence relation for the MandMGame? Yes. And here's the recurrence relation. XCK, the probability of a tie with CK M&Ms, is 1/3 XC minus 1 K minus 1 plus 1/3 C minus 1 K plus 1/3 XC K minus 1. This is a little bit more involved recurrence relation than the ones we did before. This has 2 indices, not 1. It's almost like going from Calc 1 and 2 to Calc 3. There are more powerful techniques to handle something like this, but it seems to be in the same family of what we did for the Fibonacci's, that there might be a generating function approach that would give us solutions to something like this, that there's hope, that you've related this to something you understand. However, you only were able to get that because you were smart and you saw that the neither case could be ignored, the case when neither one of them eats. What if you didn't see that? What would you have instead of a recurrence relation involving 3 terms? So if you didn't notice that you could ignore the case when neither one eats, you would have a recurrence relation with 4 terms, right? And now instead of 1/3, you would have 1/4. Oh, look, I've got an XCK on both sides. Let's subtract. I'll get 3/4. Well, let's multiply both sides by 4/3, and look, I now have the same recurrence as before. So if you weren't clever enough to notice that it was a memoryless process and you could ignore that case, as you start to do the algebra, it actually tells you, hey, something's going on here. So you really want to learn how to look at mathematics. Okay, so if we want to solve this recurrence, one way is to teach you advanced theory of generating functions of several indices. The other is to just say, we're not going to go beyond 4 or 5, so let's just do it by brute force. So we start off with x0, 0 equals 1, because if neither one has M&Ms, it's a tie. We know x1, 0 and x0, 1 are 0. And now we know from our recurrence, x1, 1 is 1/3 x0, 0 plus 1/3 x0, 1 plus 1/3 x1, 0. We know all of those. We've written x1, 1 in terms of previously known quantities. We now know x1, 1. We now know x2, 0 is x0, 2 is 0. We can now calculate x2, 1. And if we know x2, 1, we know x1, 2. And we can get x2, 1 in terms of things whose indices have a smaller sum. So think of the first one, the x0, 0, the sum of the indices is 0. The x1, 0, x0, 1, the sum of the indices is 1. Now we're looking at the sum of the indices is 2. And we can keep marching down like that. And so we can calculate x2, 2. We can keep going, and we can find the solution. All right. I'm going to skip I'm not going to say too much about this. We haven't done too much with Catalan numbers. I think we didn't do Catalan numbers in this class, right? I did them in 389, where they count how many paths are there from 0, 0 to nn where you can either move east or north, and you're not allowed to cross the main diagonal. It turns out there's a beautiful generating function attached to something like this. This is very similar. In these paths, you can only move right or up. For us, we basically have three options. We can move right, up, and we can have like a diagonal move as well. So it's a nice generalization of the catalans. All right. Here are the probabilities of a tie. K equals 1 through 8. I've done the calculations. 1/3, 5/27, 11/81, 245, 21/87. I'm not going to keep reading. What patterns do you notice? What do you notice about these numbers?
The denominator is 3.
Do you think, what about 21/87? Is that a power of 3? Yes. What about 19/683? Is that a power of 3? Yes. The denominators are all powers of 3. How do the powers of 3 go? 3 to the first, 3 cubed, 3 to the fourth. Be careful when you have a computer do calculations for you. What's 3/9? 1/3. But if the computer calculates something and the answer is 3/9, the computer might automatically simplify it for you. So when it's displaying the numbers like this, there might have been some simplifications. If there are some factors of 3 in the numerator, then it will cancel that. And so divine inspiration told me, multiply by 3 to the 2k minus 1 on the denominators. And we now get 1, 5, 33, 245, 19, 21, 15, 5, 2, 5, and so on. Okay, that looks like a really good intuition. Does anybody recognize these numbers? Does anybody know the 4 letters you should utter now? So it's the Online Encyclopedia of Integer Sequences, the OEIS. And what you do, it's an incredible website. You go to the website, you give it your sequence of integers, and it tells you everything it knows about that sequence. It'll tell you where does it know that it occurs. Here are some references, here are some formulas, here are some asymptotic behaviors, here are some defining equations. So just go to oeis.org. And it turns out that this is sequence A084771. And so this is just a start of what it will tell you. So it is the coefficients of 1 over the square root of 1 minus 10x plus 9x squared. Okay. It's also the coefficient of 1 plus, the central coefficient of 1 plus 5x plus 4x squared to the nth power. But that at least gives me something to work with. And maybe I can try to find ways to figure out what that is. Maybe I can factor things. It's also the number of paths from 0, 0 to n0 using steps of 1, 1, 1, 0, and 1, -1. Okay, that seems very similar to what we were doing. So that comment over here tells me, this could be something worth looking at. And a bunch of things over here. This is just a subset of the things it knows. So this is the power of the web, is if you have an idea of what you're trying to prove, now you have some additional sources to look at, and you might get a sense of where they come from. All right, so takeaways. Always ask questions. You have no idea where the questions are going to lead to. My son just asked, will you die on the same day? It's a really good question. And from that, we've had a lot of fun over the years. Experience is a useful and wonderful guide. Gather data. The more data you have, the more feel you have for the problem. It is extremely important to be able to look at things the right way. A lot of times the answer is there, but it's hidden. And you've got to find, how do you sniff it out from the data? I love taking logs, either on just one of the variables or on both of the variables, and all of a sudden, linear relations appear. I understand lines. On a good day, I can understand a parabola. But this reduces you to things that are much smaller. I have said this before. It's probably a good final line for the class. If all you have is a hammer, pretty soon every problem looks like a nail. Remember, what are you good at? And so if you're really good at using a hammer, whatever problem somebody gives you, try to find a way to make it look like a nail. And even better is go to the land of the screwdriver. There's smart people there. If they could have solved it with a screwdriver, they would have. If you have a different perspective, if you have another way of looking at things, you have a tremendous advantage. All right, so this is, I think, a really good place to just end the semester, just summarizing what we've done. I'm going to stop recording at this point.